Hello, my name is Stephen James and I'm a PhD student at the Dyson Robotics Lab at Imperial College London. Today I'm going to talk about RLBench, our new benchmark and learning environment for robot learning. This work was done in collaboration with Zikong Ma, David Arrojo and Andrew Davison. RLBench is a challenging new benchmark and learning environment for robot learning. The benchmark features 100 completely unique, hand-designed tasks ranging in difficulty from simple target reaching and door opening to longer multi-stage tasks, such as opening the oven and placing a tray in it. We provide an array of both proprioceptive observations and visual observations, which include RGB, depth, and segmentation masks from an over-the-shoulder stereo camera and an eye-in-hand monocular camera. Uniquely, each task comes with an infinite supply of demos through the use of motion planners operating on a series of waypoints given during task creation time, enabling an exciting flurry of demonstration-based learning possibilities. RLBench has been designed with scalability in mind. New tasks, along with their motion plan demos, can be easily created and then verified by a series of tools, allowing users to submit their own tasks to the RLBench task repository. This large-scale benchmark aims to accelerate progress in a number of vision-guided manipulation research areas, including reinforcement learning, imitation learning, multitask learning, geometric computer vision, and in particular, few-shot learning. With the benchmark's breadth of tasks and demonstrations, we propose the first large-scale few-shot challenge in robotics. We hope that the scale and diversity of RLBench offers unparalleled research opportunities in the robot learning community and beyond. For those that are in reinforcement learning, you will know that there are already many reinforcement learning environments. These include the likes of OpenAI Gym, DeepMind Control Suite, and RoboSchool, to name but a few. However, apart from a small number of robotic tasks in OpenAI Gym, these benchmarks feature only toy tasks that often do not resemble the real-world problems that robots will need to overcome. To combat this, many projects create their own manipulation tasks to evaluate their approach, making comparisons difficult. As a direct consequence of this, these created tasks can often succumb to unintentionally introducing another hyperparameter into the method in the form of the task design itself. For example, a method could fail on a more challenging task, and so results would only be presented for a simpler set of tasks. This is something a standard benchmark of tasks could alleviate. Moreover, the continuous control task in both OpenAI Gym and the DeepMind Control Suite do not provide an easy-to-use task-building tool, and so users must define tasks in XML using the Majoko interface, which can be cumbersome, error-prone, and time-consuming. This motivates the need for a one-size-fits-all benchmark that allows the capability to utilize large-scale data whilst also allowing classical systems to be compared. So what would make our ideal benchmark? When designing RLBench, we have prioritized several key properties. Diversity. The algorithms we develop should be general. In order to effectively learn inter-task relationships, a truly diverse range of tasks is needed to help avoid overfitting. Reproducibility. This is challenging in robotics as each lab has their own robotic setup. Moving to simulation solves this, but the risk of developing solutions that may not run as well in the real world. However, with the rise of deep learning methods becoming more prominent in robotics, we believe it is important to find the potential and limits of these methods in controlled, reproducible environments. Scale. Given the amount of data modern machine learning methods need, it is important not only to have a large collection of tasks, but also the ability to produce a large number of demonstrations from these tasks. Extensibility. Following on from the previous point, we hope to continue to grow this repository of tasks. Therefore, it is critical that the task-building system is easy to use. Tiered difficulty. Attempting to get robots to do a single task can be challenging, let alone expecting them to do numerous tasks. We therefore wanted to have a range of tasks, including both easy tasks such as reaching, which would be well suited to new and emerging methods, to more challenging long time horizon tasks that can stress test well-known state-of-the-art algorithms in use today. And finally, realism. Although we cannot claim full photorealism or fully realistic physics, our benchmark is much closer a match to the real world than many other training environments. The scene consists of a Franca panda fixed to a wooden table surrounded by 3 directional lights. Observations include RGB, depth, and segmentation masks from an over-the-shoulder stereo camera and an eye-in-hand monocular camera, along with the robot proprioceptive data, which includes joint angles, velocities, and torques, and the gripper pose. The arm can be easily swapped out for another arm, if required. Recently, a new front-facing camera has been added. Each task has a completely sparse reward of +1, which is given only on task completion, and 0 otherwise. Users have a wide variety of action spaces at their disposal, which include joint velocity actions, joint position actions, joint torque actions, end effector velocity actions, and finally end effector pose actions. RLBench employs 3 key terms: task, variation, and episode. Each task consists of 1 or more variations, and from each variation, an infinite number of episodes can be drawn. Each variation of a task comes with a list of textual descriptions that verbally summarize the variation of the task, which could prove useful for human-robot interaction and natural language processing research. We now motivate the need for the concept of a variation with an example. It is naturally difficult to come up with a precise way to differentiate between tasks, given their subjective nature. For example, one could argue that pick up the apple and pick up the banana are different tasks, while one could also equally argue that they are the same pick up the X task. We therefore introduce the variation concept, which allows cases like the above to be grouped as very similar tasks. Let's take a look at the figure as an example. In this case, the stacked blocks is a single task that has V variations, each with E episodes. Across variations, usually target objects or colors are changed, whereas across episodes, positions are changed. In this stacked blocks case, one variation could be stack 2 red blocks on the target, whilst another variation could be stack 1 blue block on the target. Given the way that our task building tools are designed, the variation concept allows a convenient way of getting as much from a task definition as possible, given that there is usually only a small amount of additional work needed to generate a large number of variations for a given task. So speaking of the task building tools, let's take a look at that. The task building tool is the interface for users who wish to create new tasks to be added to the RLBench task repository. Each task has 2 associated files, a Copelia Sim scene file, which holds all the scene information and demo waypoints, and a Python file, which is responsible for wiring the scene objects to the RLBench backend, applying variations, defining success criteria, and adding other more complex task behaviors. The code snippet on the left shows how simple tasks can be to build. There are many areas of research that could benefit from RLBench. These include few-shot learning, reinforcement learning, imitation learning, sim-to-real transfer, multitask learning, and SLAM and explicit model-based representations. To finish up, I'll quickly run through one of the use cases of the benchmark. In this case, a reinforcement learning agent that uses demonstrations in order to improve sample efficiency during training. First, we define what observations we want to enable and the action mode to use. Then, we can retrieve a number of demonstrations which can either be loaded from disk or generated right on the fly. We now give these demonstrations to our agent to use in some way, for example, filling a replay buffer. Finally, we train our agent. You can find much more information about RLBench in the paper, the website, or on GitHub. Links are on the slide. We hope, along with the help of the community, to continuously expand the tasks available for both training and evaluation. We hope RLBench will become a key resource for a broad range of robot manipulation-related research, and look forward to seeing what the community achieves with this diverse range of tasks. Thanks for watching.